last chapter we talked about static electricity, and we talked about neutral objects and how that charge was going to be disrupted. For example, when you scuff your feet across carpet, you touch that doorknob and get shocked. But in chapter 19 we're going to move into talking about electricity, and we're going to be talking about some of those properties associated with electric current. And then last thing we'll kind of close with is we'll differentiate between alternating current and direct current. Last chapter, when we talked about that static electricity, we said static electricity was a transfer of charges from one object to another. Like I said, when you scuff your feet across the carpet is neutral. You yourself are neutral, but because of the wool socks, as you are walking across that carpet, you're going to find out that those charges are transferred from the carpet to your feet. Those charges, because again, negatives and negatives, they want to repel one another. What they will do is they'll spread themselves out evenly amongst the object in which they were transferred to. Interactions between these charged objects and neutral objects, again, remember what we said, all neutral objects will attract to something that is charged, and the reason being is because of those particles being able to move themselves around. Electricity is going to be taking those charges, and what we're going to do is we're going to continuously move them. And the reason why we're going to continuously move them is we're going to try and operate some appliance, some device like your cell phone, refrigerator, TV, things like that. But in order to operate that device, we have to have lots of those charges, and like I said, we have to keep those charges moving. And when we get those charges moving, that's going to be an electric current. Electric current is just a rate at which electric charges move through a given area. So when we're talking about rate, what we're doing is we're talking about charges moving in a certain amount of time. Charges moving past a point in a certain amount of time. So when we talk about current, current is going to be charge divided by time. Charge, remember last chapter, was Q divided by the amount of time. So I equals Q divided by T. Q is still going to be in coulombs, okay? So if I give you microcoulombs, that's not going to work. You're going to have to convert it. Time is going to be measured in seconds. I is going to represent the current, measured in amperes or amps or an A, okay? So if we go ahead and we look at that circle equation, okay? Circle equation is going to end up looking like this. And the one that's going to go on top is going to be the Q. So we're going to have Q on top and I and T on the bottom. And then just remembering, Q or charge has to be in coulombs, time has to be in seconds, and current is going to be measured in amps. So let's continue talking about this movement of charge. Okay, moving charges that make up current can be positive, they can be negative, or they can be a combination of the two. Table 19.1 in your textbook is going to show you a comparison between charge carriers and conventional current. Positive and negative charges, so if it's made up of both of them, positive and negative charges are going to be considered charge carriers. Now, conventional current, that's going to be positive charge alone. But the thing that I want you to know, because positive charges and negative charges are opposite in charge, if they are going to be talking about current or being these charges and these charge carriers, what you're going to find out is they are going to always move in opposite directions. So if I have the positive charge moving to the right, the negative charge is going to move to the left. Okay, or if I have one going up, the other is going to be going down. So positive and negative charges or charge carriers are going to be going in opposite directions. But if I talk about conventional current, where it is positive only, every single positive charge is going to be moving in the same direction. Now the thing is, when you flip on your TV starts immediately, or when you flip a light switch, those lights turn on quickly. And the question is, why? People think that those electrons move very quickly, okay, move very fast. But the thing is, those charges or those charge carriers aren't actually moving that fast at all. What it goes back to is last chapter when we talked about electric fields. So the electric field created in the wires pushes these charges through at about 3 times 10 to the 8th meters per second. The charges themselves are very slow, but it is that field that's going to be pushing those charges through, operating whatever appliance, lights, TV, cell phone when you hit the power button and it turns on and things like that. So it's the field that's going to be causing that electricity or those charges to be operating it. Now, the thing is, we got to keep these charges moving. Okay, so there's multiple ways in which we can create this electric current. Some people use batteries. The thing popping up now is going to be wind energy, or those wind turbines, generators, things like that. When we talk about batteries, what they're doing is they're converting chemical energy to electrical energy. When we talk about a waterfall, okay, that moving water being kinetic energy or mechanical energy, converting it into electrical energy. Wind energy also is going to be that moving energy or mechanical energy, converting it into electrical energy. So what we're trying to do is we're trying to get these charges moving by having some sort of electrical energy. In an outlet, generally they supply about 120 volts of potential difference to produce that current that flows in your house. So 120 volts of potential difference. There's going to be 2 types of current. Alternating current, just like that word alternating says, back and forth. Now the thing I want you to know about alternating current, it's so fast we don't see it. I mean, when we look up at a light, you typically see light. But in reality, because of the electricity running through it, because of that alternating current, technically that current is switching directions 60 times each and every second. So it's going forward and back. So literally that light is flickering on and off. But because of the perception of it, we don't see how fast it happens. Our brain isn't able to process that to see how fast, or see that it's going off and on 60 times each and every second. Direct current, that's kind of like your batteries. There's only one direction of flow. And the thing is, that's the reason why on a battery we have positive and negative terminals. You've got your positive terminal, it leaves the positive terminal, goes all the way around, goes through whatever we're operating, game system, things like that, comes back, and it goes back into the battery. So you're going to find out that that current is only flowing in one direction. On page 699 of your textbook, figure 19.5, they show you a couple different graphs. One of the graphs that they show you, basically it's a straight line, okay, and that's your direct current, basically talking about that one flow and only one type of current going. But if you look at the other one on page 699, you kind of see a wave, a transverse wave, and what it's showing you is that back and forth movement of that electricity, okay, so forward and back.